Hello there, and welcome to the Cosmic Sleep Science. Tonight we are drifting into the quiet mystery of intelligence, a subject that sits at the center of every thought we've ever had. Intelligence is not only a human trait. It is a presence that appears in forests, in oceans, in animals with minds unlike our own, and even in the silent patterns that guide the universe. It is the strange ability to imagine, to solve, to adapt, and to create new possibilities from almost nothing. As you settle in, imagine intelligence as a hidden current flowing through everything, shaping life in ways we hardly notice. In some ways, it is familiar and comforting, and others feel so strange that they change how we see the world. It is one of scientists' greatest frontiers, and we're only just beginning to uncover its secrets. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest. Let your eyes relax. Allow your body to soften and let your mind drift gently into wonder. Let's begin. Perhaps the spark of human cleverness first flickered to life during those ancient nights when dreams grew deeper and more vivid. Picture our earliest ancestors, huddled together under endless darkness, their bodies surrendering to sleep while predators moved through the shadows nearby. Within that vulnerable state, something extraordinary was happening. The dreaming mind wandered freely through landscapes both real and imagined, weaving together fragments of memory with scenes that never actually occurred in waking life. A woman who had narrowly escaped danger during the day might find herself in sleep, running that same path again. But this time her movements flowed with greater grace, her decisions sharpened by the rehearsal. Night after night, these silent practices accumulated, refining responses without requiring the body to face real peril. The content of dreams remained strange and fluid, blending the face of a friend with the voice of a stranger, placing familiar objects in impossible locations, stirring emotions that don't quite match the scenes unfolding. Yet, within this chaos lies a workshop of the imagination. The mind experiments endlessly, testing social scenarios that haven't happened yet, preparing for threats that may never arrive, discovering opportunities hidden in the ordinary. Those individuals whose inner dream worlds offered the richest practice grounds, whose nighttime rehearsals prepared them most thoroughly for daylight challenges, may have moved through their waking hours with subtly better judgment. They might have read intentions more clearly, anticipated danger more quickly, navigated complex relationships with greater finesse. Across countless generations, these small advantages could have woven themselves into the fabric of what we now call human intelligence, transforming us into the storytelling creatures we've become. In a single night of deep, uninterrupted sleep, your brain possesses the ability to fundamentally reorganize itself. After you've spent hours wrestling with a difficult concept or practicing an unfamiliar skill, your mind doesn't simply power down when sleep arrives. Instead, beneath the stillness of your resting body, billions of tiny connections begin their delicate work of reconfiguration. Neural pathways that fired together repeatedly throughout the day strengthen their bonds, growing roots that run deeper into the landscape of your mind. Other connections, those that proved less useful or carried conflicting information, gradually weaken and fade. The process unfolds through cascades of molecular signals, each one adjusting the sensitivity of synapses with exquisite precision. These synapses are the microscopic spaces where one brain cell reaches out to touch another, passing messages through chemical whispers. During the deepest phases of sleep, your brain replays the day's activities in fast forward, running through sequences of neural firing, as though practicing a complex dance routine. You remain unaware of this internal rehearsal, yet it shapes you profoundly. A melody that your fingers stumbled over yesterday suddenly feels natural this morning. Data that seemed hopelessly tangled now arranges itself into clear patterns. Words in a foreign language that twisted your tongue just hours ago now roll forth with unexpected smoothness. Within the confines of your skull exists a city that never truly sleeps, a metropolis of cells engaged in constant renovation, tirelessly transforming yesterday's struggles into tomorrow's capabilities. This nightly editing shapes who you become, building competence from confusion, crafting mastery from mistakes. Certain creatures possess forms of intelligence so specialized that they surpass human abilities in domains we once thought were uniquely ours. When scientists design puzzles meant to measure mental capability, they typically construct them with human thinking as the gold standard. Yet the natural world quietly overturns this assumption again and again. Take the humble pigeon, an animal most people barely notice on city streets. When presented with tasks requiring the detection of subtle statistical patterns, these birds make mathematically optimal choices with remarkable consistency, while human participants in the same experiments often stumble, their judgment clouded by intuitions and narrative thinking that mislead them. Or consider certain primates who, when shown a complex array of symbols for just a fraction of a second, can recall the position of each element with accuracy that leaves human adults amazed and humbled. These aren't parlor tricks or mere reflexes. They represent genuinely specialized cognitive strengths, honed by evolutionary pressures entirely different from those that shaped human minds. While humans developed extraordinary capacities for language, metaphor, and planning across vast stretches of time, other species were perfecting their own unique forms of genius. They excel in perception, in pattern recognition, in sensory processing that captures details human awareness simply cannot hold. The tests themselves, crafted by human hands and human assumptions, become unexpected mirrors. And in those reflections, we sometimes discover that other minds shine more brightly than our own, in ways we're only beginning to appreciate before you experience the conscious sensation of making a choice. A tiny cluster of neurons has already begun tilting the scales toward one option over another. Well before that definitive moment when you feel yourself deciding, small networks tucked deep within your brain have started accumulating signals, building momentum in a particular direction, while your conscious awareness still feels completely open to either possibility. These regions, involved in preparing movements and selecting actions, show gradual changes in their electrical patterns, subtle shifts that researchers can sometimes detect and decode. This slow buildup doesn't arrive from nowhere. It emerges from the aggregation of countless influences, memories of past experiences, emotional associations, ingrained habits, contextual cues you didn't consciously notice. All of these factors begin to express themselves through neural activity that precedes the moment you'll later remember as the decision. By carefully observing these patterns, scientists can occasionally predict which button a person will press or which direction they'll choose, making their guess several seconds before the person reports having made up their mind. Consciousness, it seems, arrives like a narrator, stepping onto stage after the crucial plot point has already been set in motion. This narrator explains and claims ownership of a choice that was already underway in the deeper machinery of the mind. This doesn't erase the reality of intention or the weight of responsibility. Rather, it suggests that what we experience as decision-making is actually the surface expression of a much deeper wave of neural activity, rolling forward through layers of processing that remain hidden from our inner gaze. The development of intelligence, paradoxically, requires learning what to ignore. Every passing moment delivers an overwhelming flood of sensory information to your brain. Light streams continuously into your eyes, carrying data about millions of colors, shapes, and movements. Vibrations press against your eardrums in complex, overlapping waves. Your skin registers pressure, temperature, across its entire surface. Internal sensors report on muscle tension, organ states, chemical balances. If your mind attempted to process all of this in full detail, consciousness would grind to a halt, paralyzed by the sheer volume of input. Intelligent behavior emerges precisely when the brain learns to discard most of reality, keeping only what matters. Through experience, your nervous system discovers which patterns deserve attention and which can safely dissolve into background static. You stop hearing the gentle hum of electricity, the distant murmur of traffic, the constant pressure of clothing against skin. Your visual system stops informing you about every tiny detail in familiar environments, instead constructing a simplified model that highlights changes and unexpected elements. This compression, this strategic filtering, frees up precious cognitive resources. The brain can then focus its limited capacity on tracking meaningful changes, detecting novel patterns, identifying cause and effect relationships, and spotting opportunities. Those minds that become masters of selective ignoring build cleaner, more efficient internal models of reality. These models emphasize what matters for survival, for planning, for understanding, while quietly discarding the ocean of irrelevant detail. In the refined space created by this filtering, complex reasoning flourishes. Planning extends further into the future. Creativity finds room to play. Intelligence rises not from perceiving more, but from perceiving better, from knowing what to let fade away so that what remains can be truly understood. In the mysterious depths of the ocean, certain octopuses encounter containers they've never seen before. Vessels that hold food they can smell but cannot reach. No teacher demonstrates the solution. No instinct provides a clear answer. Yet these creatures, with bodies so different from ours and minds, organized along entirely different principles, often solve these puzzles with startling speed. 8 flexible arms, each lined with hundreds of sensitive suckers, begin exploring every surface of the container. They probe edges, test latches, investigate hinges, all while processing information through a nervous system distributed throughout their body rather than centralized in a single brain. What emerges is something that transcends simple trial and error. The octopus appears to understand the puzzle, to grasp the relationship between parts, to recognize that certain movements will produce certain outcomes. When it finally discovers how to twist a cap, slide open a compartment, or pull a stopper, the solution represents a genuine moment of problem-solving intelligence. Each arm operates with partial autonomy, conducting its own explorations and feeding information back to the central processing areas. It is as though parts of the creature's body think independently while still contributing to a unified goal. This distributed intelligence evolved along a path completely separate from vertebrate minds, arising in an ancient aquatic lineage that diverged from our ancestors hundreds of millions of years ago. The octopus reminds us that intelligence is not a single phenomenon with one true form, but rather a landscape of possibilities, each shaped by unique evolutionary histories and environmental challenges. Your brain generates creative ideas through a process that seems almost accidental, allowing signals from completely unrelated systems to mingle and merge. Deep within your skull, regions that originally evolved for very different purposes constantly communicate with each other in ways that weren't part of their original design. A region that once specialized in guiding precise hand movements now contributes to your ability to reason abstractly about tools and mechanisms. Areas that help you navigate physical space also activate when you think about social relationships, numbers, or the flow of time. When you relax and allow your thoughts to wander freely, something remarkable happens. Activity in distant, seemingly unrelated brain regions begins to synchronize, creating temporary bridges between networks that usually operate independently. Emotional memories merge with factual knowledge. Sensory impressions blend with linguistic concepts. Experiences from your distant past suddenly connect with problems you are facing today. These signals spill across the usual boundaries, meeting in association areas that function like bustling crossroads in a city, places where travelers from different regions naturally encounter each other. In these crossroads, fragments that have no obvious relationship begin to interact, creating patterns that would never appear if each system stayed in its own territory. From these unexpected collisions, new ideas spark into existence, like fire appearing when stones strike at just the right angle. A creative insight often feels sudden and complete, arriving in a flash of recognition. But underneath that subjective experience lies a slower, richer process of neural streams gradually mixing and interacting. The mind transforms these accidental meetings into deliberate innovation, turning biological quirks into sources of originality and creative power. Deep in quiet forests, individual trees live in constant communication through chemical languages of remarkable sophistication. When an insect begins feeding on a tree's leaves, breaking plant cells and triggering defense mechanisms, the tree responds within minutes. It produces compounds that make its foliage taste bitter and less nutritious, reducing the appeal to hungry insects. But the tree doesn't keep this information to itself. It releases airborne molecules that drift on the breeze, carrying a chemical message about the attack happening in its branches. Neighboring trees, even those not yet under assault, detect these volatile signals through sensors in their leaves. In response, they begin producing their own defensive compounds preemptively, preparing for an attack that hasn't arrived yet but might be coming. It is as though they've received a warning whispered on the wind, a message that allows them to mount defenses before the danger reaches them. Beneath the forest floor, an even more intricate communication network operates. Tree roots intertwine with vast fungal networks that extend through the soil like a living internet. Through these fungal partnerships, trees can transfer nutrients to neighbors that are struggling. A tree growing in a sunny patch might send sugars through the network to a companion struggling in deep shade. When a tree comes under stress from disease or drought, it can release chemical signals into this underground web, altering the behavior and resource allocation of distant trees it has never physically touched. The complexity, timing, and context sensitivity of these exchanges create patterns that resemble problem-solving and collective intelligence. Without neurons, without a central brain, without anything like human consciousness, the forest still manages to gather information, distribute it widely, and respond in coordinated ways that benefit the community as a whole. Your brain runs countless simulations of possible futures in the time it takes you to blink. Before you step off a curb into traffic, before you reach for a handhold while climbing, before you open your mouth to speak in a delicate conversation, invisible machinery in your mind flashes through dozens or hundreds of potential outcomes. In brain regions associated with memory and spatial navigation, waves of neural activity sweep through imagined scenarios at speeds far faster than physical reality could ever unfold. The mind rapidly tests different sequences of action, predicting obstacles before they appear, anticipating how other people might respond, forecasting which approaches might succeed and which might fail. Most of this processing happens entirely outside conscious awareness, compressed into moments, so brief they feel instantaneous. By the time you actually move or speak, your action carries within it the distilled wisdom of many simulated attempts, most of which you'll never remember considering. The same neural machinery supports abstract planning across much longer time scales. When you daydream about the future, your brain is running compressed simulations of events that might unfold over months or years. You imagine career changes, relationship developments, creative projects, all unspooling in your mind's eye far faster than they could ever happen in reality. These mental rehearsals allow you to harvest some benefits of experience without actually living through every risk and consequence. Each action you take in the physical world is surrounded by a cloud of unrealized possibilities, alternate versions that lived for only a heartbeat in the simulation chambers of your mind before being discarded or integrated into the path you finally chose. The intelligence that makes humans unique may paradoxically depend on neurons that fire in beautifully imperfect, unpredictable patterns. If every neuron in your brain responded to incoming signals in exactly the same way every time, your mind would operate like a perfect mechanical clock, precise and reliable, but also rigid and limited. Instead, neural firing is characterized by subtle variability and apparent randomness. The same neuron receiving what appears to be the same input might respond vigorously one moment, weakly the next moment, and not at all the moment after that. At first glance, this variability looks like a flaw, like noise interfering with a delicate communication system. But this irregularity actually expands the space of possible brain states enormously. It allows neural networks to represent subtle shades of meaning, rather than just binary yes or no categories. It enables the brain to explore slightly different responses to similar situations, maintaining flexibility while still achieving stable overall function. In this regime of structured imperfection, small changes in experience can nudge patterns of activity toward novel configurations that encode fresh insights. The mind gains a capacity to generalize from specific examples to broader principles, to handle ambiguity and uncertainty, to combine concepts in ways that have never occurred before. Intelligence grows not from eliminating the noise, but from harnessing it, from weaving this structured randomness into the fabric of thought itself. Despite possessing a brain smaller than a single grain of sand, certain bees demonstrate the remarkable ability to recognize and remember individual human faces. In the busy complexity of a garden, where flowers compete for attention and threats might approach from any direction, a bee must rapidly categorize everything it encounters. Yet these tiny creatures can learn to distinguish one human face from another with accuracy that seems impossible given their minuscule nervous systems. They don't see faces the way humans do. Instead, they break visual images down into patterns of shapes, edges, contrasts, and spatial relationships. These elements get stored as a kind of visual signature, a compressed code that captures the essential features of each face. When that same person appears again, even from a different angle or in different lighting, the bee can match the new visual input against its stored signature and recognize the individual. This ability emerges from neural circuits that contain only a few thousand specialized cells, a number so small it seems absurd that they could handle such a complex task. But the bee's brain achieves efficiency through elegant design, processing only the most informative features and discarding redundant details. The system demonstrates that intelligence doesn't require large numbers of neurons. It can arise from brilliant organization, from doing more with less, from extracting maximum meaning from minimal neural hardware. Before you consciously perceive anything, your brain has already constructed an elaborate guess about what is coming next. In every waking moment, your nervous system generates silent predictions about reality, forecasting what sounds will arrive, what images will appear, what sensations will follow from your movements. These predictions emerge from internal models built up over your entire lifetime. Models constructed from memories, learned patterns, and expectations shaped by countless previous experiences. When sensory information finally arrives from your eyes, ears, and skin, your brain doesn't simply pass it along to consciousness. Instead, it immediately compares the incoming signals to its predictions. If they match closely enough, the brain blends them together into a seamless experience, giving you the feeling of directly perceiving an objective reality. This process is so efficient that you rarely notice it happening. But the predictions aren't always correct. Sometimes the brain fills in details that aren't really there. It invents edges and boundaries to make incomplete images feel whole. It smooths over contradictions that would otherwise feel jarring or confusing. It takes ambiguous sensory input and confidently shapes it into whatever makes the most sense given your current expectations and context. This means that what you experience as reality is not a simple recording of the external world. It is a carefully crafted story, a blending of what is actually out there with what your brain expects to be there. Your sense of the present is partially created by your predictions about it, shaped by the mind's constant effort to match its internal models to the flood of incoming sensation. In the vast blue spaces of the ocean, dolphins communicate through whistles and clicks that ripple through the water like liquid music. These vocalizations aren't simple calls with fixed meanings. They possess structure, variation, and flexibility that reveal sophisticated cognitive abilities. Individual dolphins invent signature whistles that function like names, unique acoustic identities they use to call to specific companions across distances. More remarkably, dolphins can create entirely new whistles when they encounter situations or objects they've never experienced before. When faced with something novel, they improvise, crafting custom acoustic shapes that stand for these new concepts. These invented sounds then spread through the social group as other dolphins learn to recognize and reproduce them, creating a shared vocabulary that evolves in real time. This vocal creativity emerges from brains adapted for cooperation, for coordinating complex group hunts, for maintaining intricate social bonds across fluid communities that shift and change. Dolphins track relationships, remember individual histories, respond to subtle emotional cues, and communicate intentions across a range of contexts. Their expanding repertoire of whistles functions as a flexible cognitive toolkit, allowing them to form new associations and express new ideas whenever their environment presents something unexpected. The ability to generate symbolic sounds, to assign meanings flexibly, and to share these innovations socially demonstrates a form of intelligence that parallels human language in unexpected ways. Even though it emerged through completely independent evolutionary pressures in an alien aquatic realm. One of the paradoxes of learning is that genuine understanding often grows fastest in the aftermath of complete misunderstanding. When your mind forms an incorrect assumption about how something works, it creates a powerful form of cognitive tension. Your expectations clash with evidence, generating a signal that something important needs to change. This tension becomes fuel for rapid reorganization. A misunderstanding reveals the boundaries of your current knowledge with perfect clarity. It shows you exactly where your mental models break down, highlighting gaps that might have remained invisible if you'd absorbed information smoothly from the start. When the correction arrives, when you suddenly grasp where you went wrong, the shift produces a deeper and more durable understanding than if you'd learned the concept correctly the first time. This pattern appears everywhere. Children who struggle intensely with a concept before achieving breakthrough moments often retain that knowledge more firmly than those who find it easy immediately. Adults who confront mistaken beliefs and undergo the discomfort of having those beliefs challenged develop more nuanced, flexible understanding. Even artificial learning systems improve most dramatically through large prediction errors that force major updates to their internal models. The initial confusion isn't wasted time. It is productive difficulty, opening up cognitive space where new connections can form with unusual freedom. When you are lost, your mind becomes more attentive, more open to alternative perspectives, more capable of forming insights that would never emerge from smooth, frictionless learning. High in trees overlooking distant food sources, ravens face puzzles that require planning multiple steps ahead without the benefit of prior practice. A raven might see a desirable item locked inside a container or positioned where it can't be reached directly, without anyone teaching it the solution. The bird evaluates the available objects in its environment and selects tools that will enable later stages of a plan to succeed. This behavior reflects an internal simulation, a process where the raven mentally rehearses a sequence of events before physically attempting them. Rather than relying purely on instinct or trial and error, the bird imagines how different objects will behave, how obstacles can be overcome, and how its own actions will interact with the physical environment. Such foresight requires understanding causal relationships and physical principles. The raven must grasp that using one tool first will create access to a second tool, which will then enable reaching the final goal. It must hold multiple possible futures in mind simultaneously, compare them, discard the ones that lead to dead ends, and commit to the path that will ultimately succeed. In that quiet moment of planning, perched on a branch with wind ruffling its feathers, the raven demonstrates reasoning abilities that rival those of much larger-brained creatures, revealing that intelligence can achieve remarkable sophistication even in relatively small neural packages when organization and flexibility are optimized. Within the human brain, a background of irregular neural activity hums constantly, like static beneath a radio signal. Many species suppress this noise to maximize precision and reliability, but humans appear to preserve more of it, allowing a certain level of internal chaos to persist even during focused thought. This gentle turbulence creates opportunities for unlikely connections to form spontaneously. A stray memory might drift close to a current perception. A half-formed visual image might merge unexpectedly with an abstract concept you've been pondering. A melody stuck in your head might suddenly connect to a problem you are trying to solve. These encounters, born from neural noise, generate new possibilities that rigid, noise-free processing would never discover. When attention relaxes and you stop forcing your thoughts in a particular direction, this background irregularity grows slightly stronger. Your mind begins to wander through a wider landscape of associations, making leaps that seem random, but sometimes lead to genuine insights. Over time, patterns emerge from this wandering, coalescing into metaphors, inventions, stories, artistic expressions, and imaginative ideas. Creativity becomes the art of working with this controlled turbulence rather than against it, learning to shape and channel the noise into something meaningful and beautiful. The slight messiness in human neural processing, rather than being a flaw to overcome, might actually be one of the sources of our most distinctive cognitive gifts. Across the savannah, when one elephant shows signs of distress, others respond with behaviors that closely resemble compassion and empathy. An individual might be agitated by a threat, mourning a loss, or struggling with injury. Companions approach not with force or excitement, but with deliberate calm. A trunk gently reaches out, touching the distressed elephant's face or shoulder with tender pressure. Soft rumbles vibrate through the air, sounds pitched and patterned in ways that seem designed to soothe rather than alert. Sometimes multiple elephants gather around the troubled individual, offering quiet presence rather than trying to solve the problem directly. They might stand close, matching their pace to the slower individual, adjusting the group's direction of travel to accommodate someone who is struggling. These responses emerge from deep understanding of emotional states within the social group. Elephants possess extraordinary memories, tracking not just who belongs to their family, but also the history of relationships, past conflicts, moments of cooperation, losses suffered together. When one member experiences fear, grief, or pain, others seem to recognize these emotional states and respond with comfort that appears to emerge from genuine shared feeling. This emotional intelligence supports the cohesion and resilience of elephant societies, allowing families to endure droughts, predation, and environmental changes, while maintaining care for vulnerable members. Their comfort behaviors show that empathy's roots reach back through evolution far beyond primates and humans, flourishing wherever deep social bonds and complex memories intersect. Modern machine learning systems can analyze patterns in natural data so vast and intricate that human researchers would need many lifetimes to process them. While these systems don't think or understand in human terms, their capacity to detect subtle regularities creates entirely new windows into nature's hidden order. When trained on satellite imagery collected over years, they uncover rhythms in forest growth, animal migrations, and ocean current patterns that had never been noticed before. When given astronomical data, they reveal unexpected relationships between stellar phenomena separated by vast distances. These discoveries emerge not from intuition or creative leaps, but from systematic, unbiased exploration of enormous possibility spaces. The systems highlight correlations and structures too subtle or too complex for human pattern recognition to grasp naturally. They find connections buried under layers of noise, relationships that become visible only when processing millions of data points simultaneously. Scientists can then investigate these machine-discovered patterns, testing whether they represent genuine phenomena or statistical artifacts. In many cases, the patterns prove real and meaningful, pointing toward new hypotheses and fresh directions for research. This creates a powerful partnership where human creativity and machine processing work together, each compensating for the other's limitations, jointly expanding our understanding of the natural world. When presented with colored shapes, objects of varying sizes, and patterns arranged in different sequences, certain parrots demonstrate an ability that surprises many researchers. They can identify abstract rules and apply them flexibly across completely novel situations. Show a parrot two objects that match in color, and it learns not just that specific pair, but the concept of same color. Present it with objects it has never seen before, and it can correctly identify whether they match according to the learned rule. This reveals understanding of relationships rather than simple memorization. The parrot grasps that the rule transcends specific examples, functioning as a general principle that applies regardless of what particular objects appear. This capacity extends to concepts like same shape, same size, and even numerical relationships. Such abstract reasoning emerges from a combination of social intelligence, problem-solving abilities, and intense curiosity that drives parrots to manipulate objects and explore cause and effect in their environments. These same cognitive traits support their capacity for complex vocal learning and their formation of deep social bonds. As they navigate intricate social landscapes, their minds develop structures capable of handling subtle abstract concepts. What looks simple on the surface, like choosing matching items, actually reflects sophisticated internal logic and flexible thinking that many assumed required mammalian brains or primate-level intelligence. A memory isn't preserved like a photograph in an album, static and unchanging. Each time you recall an experience, the very act of remembering transforms it. Your brain reconstructs the memory from fragments distributed across many different regions, pulling together sensory details stored in one area, emotional context from another, narrative structure from somewhere else, and meaning from yet another location. During this reconstruction, the memory becomes temporarily unstable, open to modification and reinterpretation. New details might blend with original ones. Your current emotional state might shift the feeling tone of the memory. Present knowledge might alter how you understand past events. The narrative might reshape itself to fit better with your current identity and beliefs. Once the reconstructed memory settles back into storage, it carries these subtle revisions. The next time you recall it, you are actually remembering the modified version, not the original experience. This process allows memories to remain dynamic and relevant, adapting to new understanding and changing circumstances, rather than remaining frozen in a form that might no longer serve you. Through this continuous rewriting, your brain maintains a personal history that evolves alongside your growing wisdom, rather than chaining you forever to the limited perspective you held when events first occurred. Memory becomes a living process, rather than dead storage, always shaped by who you are in the present moment. In the dim waters where sunlight fades to twilight, squid have evolved nervous systems with capabilities that seem almost like science fiction. Their neurons use biochemical strategies, radically different from most other animals. Rather than being locked into the genetic instructions encoded in their DNA, squid can edit their RNA, the working copies of genes that guide protein production. This means that individual nerve cells can rewrite portions of their own genetic messages on the fly, adjusting how proteins are made to suit current environmental conditions. When water temperature shifts, when currents change, when new challenges appear, squid neurons can tweak their own molecular machinery without waiting for evolutionary changes across generations. This real-time editing allows them to fine-tune how electrical signals travel along their giant axons, maintaining precise control over their rapid movements and color-changing abilities. It gives them an adaptive flexibility that most nervous systems lack, a form of molecular intelligence operating beneath the level of conscious thought. The discovery that squid routinely edit their RNA reveals entirely new possibilities for how nervous systems can achieve flexibility and adaptation, showing that evolution has discovered multiple strategies for building intelligent, responsive minds in the ocean's depths. When you listen to music, especially music with clear structure and predictable patterns, something interesting happens to the electrical rhythms in your brain. Different regions begin synchronizing their activity, falling into coordinated patterns of firing that match the tempo and structure of what you are hearing. This synchronization can guide your neural rhythms into states that support clearer, more organized thinking. Over time, regular exposure to structured music appears to influence how your brain processes spatial relationships. The mental skills you use to track melodies, anticipate chord changes, and follow rhythmic patterns overlap substantially with the skills used to imagine rotations, understand geometric transformations, and navigate through physical space. Learning to play a musical instrument deepens these effects considerably. Practice strengthens fine motor control, sharpens auditory discrimination, and exercises working memory all at once. As these different systems train together, they become more tightly integrated, allowing your mind to form clearer mental models of spatial structure and to track complex relationships with greater ease. The influence extends beyond music itself. People who engage deeply with music often show enhanced abilities in mathematics, navigation, and other domains that require spatial reasoning. Music becomes more than entertainment or emotional expression. It quietly reshapes the architecture of thought itself. Long before sunrise paints the horizon, certain plants begin preparing for the day ahead. They adjust the orientation of their leaves, shift their metabolism, and alter their internal chemistry in anticipation of dawn. These changes occur even when plants are kept in controlled environments where light appears at completely consistent times, showing that the behavior comes from internal timekeeping rather than immediate environmental cues. Within their cells, plants maintain molecular clocks built from feedback loops of gene activation and suppression. These loops create natural rhythms that cycle with remarkable regularity, tracking the passage of roughly 24 hours even without external time signals. As dawn approaches, these internal clocks trigger cascades of changes that prepare the plant for photosynthesis. Pores in the leaves begin to open. Sugars redistribute to where they'll be needed most. Growth hormones adjust to optimize the positioning of leaves and stems. When the first sunlight finally arrives, the plant is already primed to capture and use that energy with maximum efficiency. This anticipatory behavior, driven by cellular clockwork, allows plants to survive and thrive in environments where being ready for dawn provides crucial advantages. The precision of these internal rhythms reveals a quiet sophistication in organisms that lack brains, nerves, or anything resembling central coordination. They sense and respond to patterns that extend far beyond the present moment, guided by molecular memory woven into their very cells. Within the intricate folds of your cortex, mental simulation happens constantly, mostly outside your awareness. As you prepare to speak, as you consider different courses of action, as you think through problems or plan ahead, your brain generates internal models, tiny universes where ideas can be tested without real-world consequences. These mental spaces contain fragments pulled from memory, sensory impressions, emotional associations, and abstract concepts, all woven together into miniature worlds. You can rotate objects in these internal spaces, imagine conversations, preview how choices might unfold, experiment with approaches to problems. Each simulation helps you evaluate possibilities before committing to action. When you are solving a complex problem, your mind might create multiple competing simulations simultaneously, each representing a different strategy. These internal universes rise and dissolve rapidly as your brain compares their likely outcomes, adjusting and refining until one approach feels most promising. Much of this happens so quickly and smoothly that thoughts seem to arrive fully formed. In reality, each spoken sentence, each decision, each creative idea emerges from a hidden landscape of mental simulation, from countless quiet trials conducted in the private theater of your imagination. In carefully designed experiments, crows demonstrate an understanding that seems almost philosophical. They can distinguish between different quantities of objects, including the complete absence of objects. When shown a symbol representing zero, nothing at all, they treat it as a meaningful quantity rather than a non-answer. They place it correctly in sequence with symbols representing 1, 2, 3, showing they understand that zero occupies a specific position in an ordered system. This requires more than counting. It demands abstract reasoning about the concept of nothingness as a distinct value, separate from simply not having encountered anything. When presented with varying numbers of items, crows respond differently to zero than to one, showing they perceive it as its own category with its own meaning. Such understanding helps crows evaluate situations in the wild. They might assess whether a food source has been depleted, track which areas currently offer no opportunities, or make decisions based on absence. Their grasp of zero reveals abstract reasoning abilities that many assumed required mathematical training or symbolic language, yet emerges naturally in minds shaped by survival pressures in complex environments. Within a single ant colony, thousands upon thousands of individuals move with apparent purpose, yet no central commander directs their actions. Each ant follows surprisingly simple rules based on chemical traces left by others, on chance encounters with nestmates, on local conditions it can sense directly. Yet when all these individual behaviors combine, something remarkable emerges. The colony as a whole displays coordinated strategies and problem-solving abilities that transcend anything a single ant could comprehend. Temperature regulation within the nest happens through collective adjustment. When the interior grows too warm, ants position themselves to create airflow through elaborate tunnel systems. They don't understand thermodynamics, yet their combined movements generate effective climate control. When food sources appear in the environment, the colony discovers efficient routes through a kind of distributed computation. Successful paths gain stronger chemical reinforcement as more ants follow them, while less productive routes gradually fade. When threats approach, defensive responses emerge that shift dynamically based on the size, location, and persistence of danger. Individual ants can't assess these factors comprehensively, but the colony as a whole responds with tactical flexibility. This distributed intelligence arises without hierarchy, without planning, without anything resembling conscious strategy. Information flows through continuous chemical exchange, through physical contact, through the movements of thousands of tiny bodies, acting as nodes in a living computational network. The colony becomes something greater than the sum of its parts. A collective mind that adapts, learns, and solves problems through the elegant simplicity of countless small interactions woven together. Perhaps human intelligence strengthened and deepened because our distant ancestors discovered the power of narrative. Long before writing systems emerged, before permanent settlements formed, before agriculture transformed human societies, people gathered together and told stories. Around fires that pushed back the darkness, voices carried tales of hunts, of dangers encountered, of resources discovered, of conflicts and alliances, of the dead and the divine. These shared narratives did something extraordinary. They allowed knowledge to accumulate beyond what any individual could experience directly. A young person could learn about a distant water source from an elder's story, gaining survival information without the danger of exploration. Hunters could share strategies that had worked or failed, building collective wisdom that improved with each retelling. Social lessons embedded themselves in cautionary tales and heroic examples. Over countless generations, this cultural transmission created a form of memory that lived outside individual minds, carried forward through language and story. Those communities whose members excelled at storytelling, who could craft narratives that taught clearly and were easily remembered, gained advantages. Their collective knowledge grew richer and more detailed with each passing generation. Minds that could create compelling stories, that could extract meaning from events and weave them into memorable narratives, that could imagine the experiences of others vividly enough to learn from them. These minds thrived. Storytelling encouraged the development of empathy, of abstract thinking, of the ability to manipulate symbols and meanings. It rewarded creativity, memory, and the capacity to understand cause and effect across time. Intelligence became intertwined with narrative ability, transforming humans into creatures who don't just live in the world, but who constantly interpret it, explain it, and share those interpretations through the ancient and powerful medium of story. Across vast stretches of ocean, whales fill the water with vocalizations so complex they challenge our understanding of animal communication. These aren't simple calls. They're layered compositions containing multiple levels of structure, with basic units combining into longer phrases, phrases arranging into extended themes, themes flowing into songs that can continue for many minutes. Some whale species modify their vocalizations in response to companions, adjusting timing, pitch, and rhythm in what appears to be a form of conversation. The complexity resembles aspects of language because meaning emerges not just from individual sounds, but from patterns across time, from sequences and arrangements that carry information beyond what any single element could convey. Different populations develop distinct vocal traditions, creating regional dialects that mark social groups and geographic areas. Young whales learn these patterns from adults, absorbing the cultural variations of their community. Over time, songs evolve gradually, with new elements appearing and spreading through populations, as individuals introduce innovations that others adopt. These layered communication systems allow whales to coordinate movements across distances we can barely imagine, to maintain social bonds when separated by miles of empty ocean, to convey information about individual identity and emotional state. Their songs become both practical tools and cultural expressions, carrying traditions forward through generations in the lightless depths. During the ordinary activities of daily life, your brain constantly absorbs patterns you never consciously notice. Statistical regularities hide in every stream of sound, every sequence of visual images, every flow of events. Your nervous system detects these regularities automatically, building implicit knowledge that shapes your behavior without ever entering awareness. When you hear language, even language in an unfamiliar accent or context, your brain tracks which sound combinations appear frequently and which rarely occur. You absorb the rhythm of speech, the statistical likelihood of certain syllables following others, the common cadences and pauses. None of this reaches consciousness as explicit learning, yet it profoundly influences how you perceive and produce language. The same implicit learning happens with motor skills. Your body discovers subtle patterns in how movements combine most efficiently, how timing affects outcomes, how small adjustments improve performance. You improve at activities without being able to articulate what you've learned. Social situations also generate hidden patterns. Through thousands of interactions, you absorb regularities about how people typically respond, about which conversational moves lead, about the unspoken rules governing different social contexts. This knowledge guides your intuitions and gut feelings, operating through pattern recognition systems that work beneath deliberate thought. The brain becomes a constant, tireless student of statistical structure, learning from the flood of experience without requiring conscious effort, building models of reality that capture the hidden order in seemingly chaotic environments. Deep in rainforests where water trickles through moss and fog drifts between tree trunks, certain frogs navigate with uncanny precision. When researchers place these frogs in complex mazes or unfamiliar territories, they often choose routes with remarkable efficiency, moving toward goals through twisted paths with fewer errors than chance would predict. Scientists have attempted to understand what sensory information guides them, testing whether vision, scent, or sound could account for their accuracy. Yet, these known senses don't fully explain the frog's navigational abilities. The animals seem to draw on additional sources of information, possibly detecting subtle gradients in humidity that shift across the landscape, or sensing variations in electromagnetic fields generated by water flow and earth conductivity, or perceiving spatial information through mechanisms hidden in their skin's moisture sensors or their inner ear's balance systems. Whatever combination of senses they employ, the result is a form of environmental awareness that allows them to build mental maps of their surroundings with impressive detail. They move through the forest not by random exploration, but with apparent purpose, as though consulting an internal representation of space that captures information invisible to human perception. Their navigation hints at the existence of sensory worlds we haven't fully discovered, ways of knowing the environment that evolution has crafted, in lineages far from our own, suited perfectly to the specific challenges of their habitats. When you find yourself stuck on a difficult problem, when focused concentration seems to produce nothing but frustration, something interesting often happens if you step away. As your attention shifts to something else, as your mind begins to wander, the stubborn problem sometimes suddenly yields. Solutions appear seemingly from nowhere. Insights crystallize with unexpected clarity. Approaches that felt impossible moments earlier now seem obvious. This happens because mind-wandering activates different neural networks than focused concentration. When you deliberately focus, certain executive control systems dominate, holding attention steady and suppressing distractions. This works well for many tasks, but it can also create mental rigidity, making it harder to see problems from new angles. When your mind wanders, activity shifts toward networks that make distant connections, that allow memories from different contexts to surface and interact, that permit unusual associations to form. A smell might trigger a childhood memory that somehow relates to your current challenge. A sound might activate a concept learned long ago that suddenly seems relevant. Random thoughts drift across your awareness, some meaningless, but others carrying fragments that combine into new perspectives. The wandering state provides a form of mental exploration, searching through possibility space more freely than directed thinking allows. Connections that focused attention would suppress as irrelevant or distracting can emerge and prove valuable. What looks like mental idleness from outside is actually a different mode of problem solving, one that accesses creativity and insight through relaxation rather than effort. In arid lands where sun beats down relentlessly and rain arrives unpredictably, termite mounds rise like earthen cathedrals. These structures, built grain by grain over months and years, function as sophisticated climate control systems created entirely through collective behavior. Millions of tiny workers, each following simple local rules, combine their efforts to construct ventilation networks of startling complexity. Individual termites respond to temperature and humidity in their immediate vicinity. When an area feels too warm, they carry soil to create barriers or openings that redirect airflow. When moisture accumulates, they adjust passages to improve evaporation. When air grows stale, they modify channels to enhance circulation. No termite understands the overall design. Each simply responds to local conditions with small actions. Yet from these countless small decisions, a functional architecture emerges. Air flows through the mound in patterns that stabilize internal temperature within narrow ranges. Despite wild fluctuations outside, hot air rises through certain channels, while cooler air is drawn in through others. Moisture distributes evenly. The inner chambers where the colony grows its fungal gardens remain remarkably constant in their conditions. The mound adjusts continuously as seasons change. New passages open when needed, old ones close when no longer useful. The structure behaves like a self-regulating system, measuring and balancing climate through nothing more than instinctive responses woven together at massive scale. The colony's collective intelligence creates what no individual termite could design or comprehend. Even before they understand a single word, human infants demonstrate surprising sophistication in processing patterns. When babies only a few months old watch shapes appearing on screens or hear streams of syllables, their eye movements and attention patterns reveal impressive statistical learning. They track which events tend to occur together, which sequences appear frequently, which combinations are rare or unexpected. When something violates the emerging patterns their brains have detected, babies show it through their attention. Their gaze lingers slightly longer on impossible events or unexpected sequences, as though something doesn't quite fit their developing model of how things should work. They have no language to describe what surprises them, no explicit understanding of what they've learned. Yet their nervous systems clearly distinguish between probable and improbable events. This sensitivity helps infants discover structure in the chaos of sensory experience. Before anyone teaches them grammar, they're detecting statistical regularities in speech that allow them to identify where words begin and end in continuous streams of sound. Before they understand object permanence conceptually, they're noticing patterns in how objects behave and interact. The infant brain operates as a powerful pattern detection engine, quietly tallying frequencies and probabilities, building implicit models of reality through exposure alone. This foundation of statistical learning supports everything that comes later, providing scaffolding for language, for understanding cause and effect, for navigating the physical and social world, drifting through ocean currents, translucent jellyfish pulse with deceptive simplicity. They possess no centralized brain, no structure that obviously corresponds to what we think of as a mind. Yet certain species exhibit behaviors that change based on experience in ways that resemble learning. When jellyfish repeatedly encounter obstacles in their environment, when they experience particular patterns of light or water flow, their subsequent movements begin to shift in lasting ways. The distributed networks of nerve cells scattered through their bell-shaped bodies respond differently after prior exposure to stimuli. Their pulsing rhythms adjust. Their directional movements change. They navigate around obstacles more efficiently than before, as though some trace of past encounters influences present behavior. There is no memory center storing these experiences. Instead, Rings of interconnected nerve cells seem to hold temporary changes in their response properties. Recent events leave molecular traces that alter how subsequent signals propagate through the network. When conditions shift again, the patterns of activity shift with them, creating a primitive form of adaptation. This suggests that the capacity to learn from experience doesn't require complex brain architecture. It can emerge from relatively simple nervous systems where signals ripple through living tissue, where even small persistent changes in how cells communicate can gradually adjust behavior in ways that help the organism survive. Every waking moment delivers far more information than your brain could possibly process in full detail. Light floods your retinas with data about millions of points of color and brightness. Sound waves carry layered acoustic information. Touch, smell, taste, internal sensations all generate continuous streams of input. If your nervous system tried to maintain all of this in conscious awareness, thought would be impossible. Instead, your brain performs extraordinary compression. Chains of neurons transform these overwhelming floods of detail into compact representations that preserve essential information while discarding vast amounts of redundancy. Groups of cells fire together in specific patterns that encode edges, textures, movements, meanings, all in highly efficient codes. A familiar face reduces to a particular constellation of neural activity that captures identity without storing every pixel of visual detail. A remembered location becomes a compressed sequence that can later reconstruct a mental journey without preserving every step. A complex idea condenses into a symbol or phrase that carries rich meaning in minimal form. This compression isn't simple data reduction. It is intelligent selection, preserving information that supports understanding and action, while eliminating background noise and irrelevant detail. When you recall an event, relatively small patterns of activity in key brain regions can trigger the reconstruction of sounds, images, emotions, and context with surprising vividness. Intelligence depends fundamentally on this ability to compress experience into efficient neural codes, creating mental representations that capture the essence of reality without drowning in its infinite detail. Across frozen tundra and through dense forests, wolf packs move with coordinated precision that seems almost telepathic. Yet their coordination emerges not from vocal commands, but from constant visual attention to subtle signals. Every pack member watches the others continuously, tracking positions, speeds, and tiny shifts in posture or direction. During a hunt, when prey suddenly changes direction, you might see one wolf on the far flank quicken its pace or angle slightly outward. This small movement prompts companions to adjust their positions, perhaps tightening formation or spreading wider. No sounds pass between them. The coordination happens through vision and learned interpretation of movement patterns. Young wolves absorb this communication system through observation. They follow older pack members on hunts, watching how experienced hunters position themselves, learning to read meaning in each postural shift and directional change. Over time, the pack builds a shared vocabulary of movement, each gesture carrying significance that comes from repeated hunts and their outcomes. These subtle signals allow the group to adjust tactics fluidly as situations unfold, to exploit terrain and wind, to respond to unpredictable prey behavior. The wolves function as a coordinated unit without needing complex vocalizations, turning individual awareness into collective intelligence through the simple but powerful channel of observed movement. Buried deep in your brain, regions that now help you imagine tomorrow and plan for next year originally evolved to solve a different problem entirely. Early humans needed to navigate complex social worlds, to remember who could be trusted and who might betray, to anticipate how others would react to different actions, to imagine the consequences of sharing resources or withholding them. These demands strengthened neural circuits capable of constructing mental scenes of events that hadn't happened yet. Over time, these circuits expanded beyond their original social purpose. The same networks used to imagine a companion's likely response could now model the outcome of a journey into unfamiliar territory, could preview how building a new shelter might unfold, could anticipate the results of changing hunting strategies. As language developed, These imagined futures became easier to describe and share, allowing groups to coordinate around possibilities that existed only in collective imagination. The ability to plan cities, to develop technologies, to create complex cultural institutions, all draw on neural machinery, originally shaped by the need to predict social dynamics in small bands of foragers. Your capacity to envision tomorrow emerges from ancient adaptations for understanding other minds, revealing how evolution repurposes existing structures for new challenges. Beneath warm tropical waters, coral reefs extend like living cities built from countless tiny polyps. Each polyp is a simple organism, feeding and growing according to local conditions. Yet the reef as a whole exhibits collective responses that look strikingly like coordinated decision-making. When environmental stresses appear, when water temperature rises or nutrient levels shift, chemical signals spread through the reef's interconnected tissue. Different sections adjust their behavior based on both local conditions and signals from neighbors. Some areas reduce growth to conserve energy during stress. Others increase repair activities to counter damage. Polyps modify how they share nutrients with the symbiotic algae living in their tissues, adjusting this crucial relationship to match changing conditions. These adjustments aren't directed centrally. They emerge from distributed interactions as each polyp responds to its immediate environment, while also sensing and responding to the altered states of surrounding polyps. The result resembles collective negotiation, where the reef as a whole selects strategies through countless small acts of chemical communication. In this way, reefs perform something similar to group decision-making, balancing competing demands, allocating resources toward areas of greatest need, maintaining stability through coordination that requires no central coordinator, only constant exchange of signals through living tissue. When you observe someone else experiencing an emotion, when you watch a face contort in pain or light up with joy, something remarkable happens in your own brain. Neural regions involved in your own emotional experiences activate as if you are feeling a muted version of what you are observing. Motor areas associated with making particular expressions show activity even though your own face remains still. Your brain essentially simulates the other person's state using its own neural machinery. It runs a quiet internal model, borrowing its own patterns of emotional and physical response, and reshaping them to match what it observes externally. This simulation provides intuitive understanding that goes beyond logical inference. Through these echoes, your mind constructs an internal portrait of another person's perspective and feelings. Every interaction, every conversation, every moment of connection adds detail and refinement to the internal models you maintain of others. Over time, you develop the ability to sense confusion, guardedness, honesty, hidden distress, often from cues so subtle you can't consciously articulate what informed your intuition. This capacity to simulate other minds using pieces of your own mind supports empathy, cooperation, teaching, and the intricate negotiations of social life. It represents a form of intelligence built on the foundation of self-awareness, using the self as raw material for understanding those who exist outside the boundaries of your own experience. In groups of monkeys and apes that share food, grooming, and protection, individuals pay careful attention to fairness in exchange. When two companions perform similar tasks and one receives a more desirable reward, the other may refuse its lesser offering, turn away from the experimenter, or display clear signs of protest and agitation. This reaction costs something immediate, since rejecting food provides no short-term benefit and might mean going hungry. Yet it sends a clear social signal. By reacting strongly to unequal outcomes, the animal asserts an expectation that cooperation should yield roughly balanced returns over time. These responses can discourage exploitation, encouraging more equitable treatment within the group. Young monkeys observe these exchanges carefully, gradually developing their own sensitivity to fairness and unfairness. They absorb standards about what constitutes acceptable sharing, learning that relationships depend on reciprocity and reasonable balance, rather than purely on dominance and submission. This early form of fairness emerges organically from the pressures of living closely with others, where long-term stability depends on mutual regard. It doesn't require language, formal rules, or abstract reasoning about justice. It arises naturally from social emotions and memory, from the need to maintain cooperation across time. When advanced computational systems explore vast mathematical spaces, testing countless combinations and relationships, they sometimes uncover patterns that no human mathematician has ever described. These systems move through territories too large and complex for human intuition to navigate efficiently, checking possibilities that would require lifetimes of manual exploration. As they search, they occasionally discover hidden regularities, unexpected symmetries, surprising connections between mathematical objects previously thought to be unrelated. These discoveries often appear strange at first, solutions or patterns that don't match human aesthetic expectations about how mathematics should work. Yet, when human mathematicians examine these machine-discovered structures, they often find genuine insights buried within them. The patterns prove to be mathematically valid and sometimes profoundly interesting, pointing toward new theorems or revealing unexplored regions of mathematical landscape. This creates a productive partnership. Machines provide tireless exploration and pattern detection at scales impossible for humans. Humans provide interpretation, intuition, and the ability to recognize which discoveries matter and why. Together, they expand the boundaries of mathematical knowledge faster than either could alone. Hidden within the intricate networks of your brain are specialized cells that shape how electrical signals flow and propagate. These cells don't simply pass messages along. They modulate signals with exquisite precision, strengthening some while dampening others, speeding some while delaying others, creating intricate patterns of timing and intensity. Their influence resembles a subtle language spoken between neurons, a language made not of words but of carefully controlled voltages and precisely timed impulses. By adjusting signal flow, these modulatory cells determine how memories link together, how attention shifts between different streams of information, how meaning emerges from raw sensation. They help your brain transition smoothly between different states of consciousness, between focused attention and relaxed awareness, between emotional engagement and analytical detachment, between habitual responses and creative insight. Without their constant regulation, neural processing would become either rigidly mechanical or chaotically unstable. Their presence creates layers of nuance in every thought and feeling. They enable the flexibility and depth that characterize human intelligence, allowing the mind to adjust its own processing dynamically in response to changing demands. In clear aquarium tanks and coral reef environments, certain fish species demonstrate a capacity that was long thought to be uniquely primate. When they encounter their reflection in a mirror, they eventually begin to behave as though they recognize the image as themselves rather than another fish. If researchers place a visible mark on the fish's body, it will attempt to remove the mark after seeing it in the reflection. This behavior requires more than simple visual processing. It demands an internal representation of self, some sense of personal boundaries and appearance that allows the fish to distinguish its own body from others. The fish must understand that what it sees in the mirror corresponds to itself, that the mark visible in the reflection belongs to its own body. When fish inspect themselves repeatedly, adjust their posture to view themselves from different angles, and show purposeful attempts to address marks they can only see in reflection, they reveal cognitive sophistication that challenges assumptions about where self-awareness begins. In the shifting light of a mirror, a fish's mind encounters itself and responds with apparent recognition. Your brain constantly seeks patterns and connections, even in randomness. When presented with scattered information, with events that have no underlying relationship, your mind still attempts to weave them into coherent narratives. This tendency runs deep, emerging from evolutionary pressures that rewarded finding patterns even when they were faint or ambiguous. Early humans benefited from detecting structure in their environment, from noticing that certain clouds preceded rain, that particular sounds signaled danger, that specific sequences of events tended to repeat. Those who saw patterns, even occasionally seeing them where none existed, often survived better than those who missed genuine patterns. Over time, this bias toward pattern detection became fundamental to how your brain processes information. When you see familiar shapes in clouds, hear meaningful words in random noise, find significance in coincidences, you are witnessing this deep drive to impose order on chaos. The tendency can lead to false conclusions and superstitious thinking, but it also fuels creativity, imagination, scientific hypothesis formation, artistic expression. Your mind's compulsion to create stories from fragments, to find connections between disparate elements, drives both error and insight, both confusion and understanding. Within dark caves and across moonlit skies, bats share knowledge through close social contact in ways that create cultural traditions. When one bat discovers a new feeding strategy, perhaps a novel way to extract nectar from a challenging flower, or an innovative approach to catching particular prey, others observe and learn through demonstration. Young bats pay special attention to experienced adults, following them during foraging flights and carefully watching their techniques. They attempt to replicate the movements and approaches they observe, practicing until they master the skill. Over time, successful innovations spread through the colony as more individuals adopt them. These learned behaviors become part of the colony's cultural inheritance, passed not through genetic information, but through social learning and imitation. Different colonies develop distinct traditions, local variations in technique that mark them as separate communities, even when environmental conditions are similar. This transmission of knowledge allows bat colonies to adapt to environmental changes with impressive speed. New food sources can be exploited quickly once one individual discovers an effective approach and shares it, intentionally or not, with companions. Human curiosity intensifies when the mind encounters something that violates expectations, when reality doesn't match what your brain predicted. In that moment of mismatch, neural systems associated with attention and learning surge into higher activity. Your mind becomes more receptive, absorbing information with greater depth and retention than it does during routine, predictable experiences. This spike in engagement happens in the gap between what you know and what you've just encountered. In the space between expectation and reality, the brain treats this gap as important, as information that could update and improve its models of the world. Curiosity emerges as the drive to explore that gap, to resolve the mismatch, to understand why reality differed from prediction. These moments often shape lasting interests and passions. A child's curiosity sparked by an unexpected observation might lead to a lifelong fascination with a subject. An adult's surprise at encountering something that doesn't fit their understanding might redirect their career or thinking in entirely new directions. Curiosity functions as both compass and fuel, pulling the mind forward whenever familiar patterns break down and the horizon shifts unexpectedly. Despite lacking even a single neuron, slime molds navigate complex mazes with surprising efficiency. When placed in a labyrinth with food positioned at the exit, the organism spreads through every available pathway, exploring the space thoroughly. Then, over time, it withdraws from dead ends and channels its growth along the route that leads to food most directly. This process resembles memory, but instead of being stored in neural tissue, it is encoded in the changing shape and chemical composition of the organism itself. As the slime mold extends pseudopods into different paths and then retracts them, it leaves subtle chemical traces. These traces influence where future growth occurs, creating a form of spatial memory written in living tissue. Each advance and retreat adjusts the organism's internal chemical landscape, gradually building a map of which paths lead somewhere useful and which lead nowhere. The slime mold's body becomes both the storage medium and the computational processor, learning through physical reconfiguration rather than through neural activity. This reveals that intelligence and memory can emerge from the simplest biological materials when organized appropriately, that learning doesn't necessarily require brains or nervous systems. Deep within your brain, specialized networks generate rhythmic patterns of electrical activity that pulse like silent music. These rhythms help organize spatial information, allowing your mind to track locations, distances, boundaries, and routes. As you move through an environment, internal rhythms synchronize with sensory input and motor commands, creating stable mental maps that persist even when you close your eyes. The rhythms provide a temporal scaffold for memory, helping you recall not just where things are, but in what sequence you encountered them, how far you traveled, which paths you took. They shift subtly as you change speed or direction, adjusting the mental representation of space dynamically. These neural oscillations create structure in how spatial information is processed and stored. Without them, navigation would become confused and disorganized. The rhythms bind together different aspects of spatial experience, memories of places with memories of movement, visual landmarks with felt distances. Your brain sings these silent songs constantly as you move through the world, using rhythm to map reality. Large predators teaching their young create relationships that resemble traditional apprenticeships. In grasslands and forests, young hunters learn through guided practice that extends far beyond simple observation. Adult predators demonstrate stalking techniques, showing how to use terrain and wind, how to approach without sound, how to time attacks precisely. They allow juveniles to attempt difficult tasks while remaining close enough to intervene if serious danger develops. Each lesson introduces new challenges, building skill progressively. The young watch every detail, absorbing how experienced hunters read animal behavior, judge distances, coordinate with others during group hunts. These teaching sessions continue long after young predators can perform basic hunting behaviors, showing that mastery requires extended mentorship rather than just instinctive knowledge. The learning process transfers knowledge through demonstration and practice, rather than through genetic inheritance. Each generation receives a richer foundation for survival because knowledge accumulates across lifetimes, refined and passed forward through the relationship between teacher and student. Human language may have roots in playful experimentation with sounds and gestures, begun not out of necessity, but out of simple joy. Before words carried established meanings, early humans likely played with vocalizations and movements, simply because they found pleasure in the activity itself. They mimicked sounds from their environment, created rhythms, experimented with new noises. Companions noticed these playful productions, and sometimes imitated them, creating shared games of sound and gesture. Over time, certain patterns began to be associated loosely with common experiences or objects, not through deliberate naming, but through repeated playful coincidence. Play provided a safe space for experimentation, allowing individuals to try new forms of expression without fear of making mistakes or facing consequences. It encouraged imitation, variation, elaboration. Groups began developing shared symbolic systems rooted in enjoyment and curiosity, rather than utilitarian communication. Gradually, these playful experiments gained structure and consistency. From casual mimicry emerged pattern. From shared pleasure emerged meaning. Language may have begun as imaginative play long before it became the complex communication system that now carries human thought across time and space. When certain spiders hunt, they engage in behavior that looks remarkably like strategic planning. Before moving toward prey, they explore their environment extensively, inspecting multiple pathways, testing surfaces, examining angles and shadows. Rather than simply rushing forward, they pause to evaluate different approaches. Their movements shift from rapid exploration to deliberate consideration. They may test one route partially, retreat, try another, then commit to a path that requires several sequential moves before reaching an advantageous position. Some individuals inspect an area carefully, retreat to concealment, and later return following the specific route they selected earlier. This reveals an internal process that stores temporary information about locations, opportunities, and strategies. The spider coordinates multiple decisions in sequence, suggesting a level of planning that goes beyond simple stimulus-response behavior. Each choice builds on previous ones, working toward a goal that won't be reached until several steps have been completed. In the quiet world between leaves and branches, these small hunters make decisions that unfold like tactical plans, revealing unexpected cognitive depth in creatures with nervous systems, tiny compared to vertebrate brains. Your visual system responds to movement before it identifies what is moving. The instant something shifts in your field of view, Specialized neural pathways react to the change even before your conscious mind recognizes the object. This rapid motion detection comes from ancient circuits evolved to respond immediately to potential threats or opportunities. These circuits process direction and speed with remarkable quickness, allowing your body to prepare for action before conscious recognition forms. Only after this initial wave of motion processing does your brain piece together shape, color, texture, and identity. This two-stage processing gives significant advantages. Motion draws attention to areas that matter most, guiding your gaze and sharpening perception where it is needed. Your emotional and motor systems can begin preparing responses, while the slower identification processes work on determining exactly what moved. The deep layers of visual processing reveal that detecting movement isn't a refinement added onto object recognition, but rather one of vision's most fundamental and ancient purposes, present in nervous systems long before the ability to recognize complex forms evolved. When apes modify tools, they reveal understanding that goes beyond surface observation. They don't simply use objects they find, they actively reshape them, adjusting weight, length, texture, and form to match task demands. A branch might be shortened for better control, stripped of leaves to improve grip, or sharpened to extract insects from narrow holes. These modifications show that apes reason about hidden properties like strength, flexibility, and leverage. They seem to understand that changing an object's form will change how it behaves, that certain invisible characteristics determine whether a tool will succeed or fail. In experimental settings, apes choose tools that can reach beyond their direct grasp, alter materials to improve their function, and sometimes combine objects in novel ways to create forms they've never encountered before. These actions suggest they can imagine how a tool will perform before actually using it. This ability creates links between animal cognition and human technological thinking, showing that the foundations of invention extend deep into our evolutionary history, present in minds that share our ancient heritage. Moments of insight often correlate with the brain entering unusual states where normal patterns of activity reorganize themselves temporarily. Inside your skull, countless neural networks maintain their own characteristic rhythms and firing patterns. When insight strikes, the system briefly shifts into a fluid condition where these patterns loosen and recombine in unexpected ways. This state exists between rigid order and complete chaos. It is stable enough to maintain function, but flexible enough to allow novel connections. During these moments, information stored in separate regions can suddenly interact, creating relationships the mind hadn't considered before. People experience this as sudden clarity. A problem that seemed impossible becomes simple. A connection that was hidden becomes obvious. The shift doesn't result from more effort. It comes from the brain allowing itself to enter a more flexible configuration where ideas can reorganize freely. Once the insight crystallizes, neural activity settles again into more stable patterns, but now holding the new understanding. Insight emerges from the brain's capacity to temporarily relax normal constraints and explore different internal arrangements. Despite having brains a fraction of the size of mammalian brains, certain birds perform logical reasoning tasks with remarkable sophistication. Their small skulls contain neurons packed with extraordinary density, arranged in efficient networks that support complex cognition. These structures allow birds to understand relationships, evaluate evidence, and make decisions based on logical rules. Experiments reveal that some birds can identify whether items match abstract criteria, select correct answers from multiple options, and comprehend relational concepts like larger than or same as. Their success emerges from genuine reasoning rather than memorization or simple conditioning. They solve problems using internal strategies that reflect structured thinking, demonstrating that intelligence doesn't depend on brain size or cortical layers. What matters is organization, connection density, and network efficiency. In small heads and quick movements, powerful cognition reveals itself, challenging assumptions about the relationship between brain architecture and mental capability. Within coral colonies, Individual polyps share resources in patterns that suggest rudimentary planning. When environmental conditions shift, when light or temperature or nutrients change, polyps adjust how they store and distribute energy. Some transfer resources toward sections requiring urgent support, such as areas recovering from damage or regions receiving insufficient sunlight. Others temporarily reduce their own metabolic demands to help stabilize the colony as a whole. These transfers follow patterns shaped by chemical signals, environmental feedback, and interactions between neighboring polyps. Over time, the colony's behavior resembles a system making allocation decisions, investing where returns will be greatest for collective survival. This coordinated resource sharing reveals distributed intelligence emerging from simple units working in harmony. It shows how life can engage in something resembling planning without any central planner, using communication and cooperation to maintain balance in shifting underwater worlds. Human genius often manifests through the ability to combine ideas from completely unrelated domains. When most people encounter concepts that seem to have nothing in common, they keep them mentally separated. But certain minds do something different. They blend the unrelated ideas, forcing them into conversation, creating hybrid concepts that didn't exist before. This combination generates inventions, theories, artistic works, and insights that feel strikingly original. Genius thrives on these unexpected marriages of thought. The mind searches for hidden links between disparate fields, allowing technical knowledge to merge with artistic sensibility, scientific understanding to blend with philosophical inquiry, practical skills to combine with abstract imagination. Many breakthroughs in human knowledge have emerged from individuals who refused to honor the boundaries between disciplines, who imported ideas from one domain into another, where they'd never been applied before. This ability to cross boundaries and mix categories represents a crucial aspect of creative genius. Sea lions learning syntax, like rules, demonstrate cognitive abilities once thought uniquely human. During training, sea lions learn that certain elements in a sequence must appear in specific orders for the sequence to be correct. They understand that relationships between elements matter, not just the elements themselves. When presented with new symbols they've never seen before, arranged according to the learned rules, sea lions evaluate the sequences correctly. They respond positively only when the structure matches the pattern they learned, showing sensitivity to abstract relationships rather than concrete memorization. This reveals understanding of structure analogous to grammatical rules in language. Although sea lions don't speak, their ability to process ordered relationships highlights cognitive competence that mirrors aspects of human linguistic ability. Their minds navigate patterns with an elegance that resembles syntactic reasoning. As your brain develops from infancy through adulthood, it creates far more neural connections than it will ultimately keep. This initial overabundance gets sculpted through a process of selective elimination. Connections that prove useful, through repeated activation, grow stronger. Those that remain inactive or conflict with effective patterns gradually weaken and disappear. This pruning process paradoxically makes the brain smarter by making it simpler. Removing excess connections allows signals to travel more efficiently, thoughts to form more precisely, patterns to emerge more clearly. The brain becomes a refined network shaped by experience rather than an overgrown tangle of every possible connection. Pruning continues throughout life, guided by what each person encounters and practices. Intelligence emerges not from preserving every connection, but from strengthening what matters, while eliminating what adds noise or confusion. In several primate communities scattered across different forests and regions, individuals maintain behaviors that differ dramatically from one group to another, despite living in similar environments. These variations represent cultural traditions passed down through social learning rather than genetic inheritance. Elders demonstrate techniques for processing foods, using tools, resolving conflicts, and navigating social hierarchies. Young members observe intensely and practice until they master each tradition. Over time, these learned behaviors evolve, gaining new refinements or variations. They form the collective identity of each group, shaping how members interact and cooperate. When researchers compare different groups of the same species, they find distinct cultural profiles, evidence that knowledge lives not just in individual minds, but in the shared practices of communities, carried forward across generations through teaching and imitation. Human intelligence may strengthen when we encounter ideas that challenge our existing beliefs. When comfortable viewpoints face contradiction, the brain shifts into heightened evaluative states that promote cognitive flexibility. This encounter disrupts automatic thinking patterns and forces deeper examination of assumptions that usually operate invisibly. As the mind works to integrate conflicting perspectives, neural networks that typically remain separate begin interacting more vigorously. These interactions forge new pathways that expand understanding. Over time, repeated exposure to challenging ideas encourages development of more nuanced reasoning and improved emotional regulation. This process doesn't weaken conviction. It enriches understanding by prompting the brain to refine and reorganize what it knows, creating more complex and resilient models of reality. Across sprawling colonies beneath the earth and along forest floors, ants move with coordinated purpose that belies their tiny size. Each individual ant follows simple chemical rules, depositing and detecting pheromone trails that guide their movements. When an ant discovers food, it returns to the nest while laying down a chemical marker. Other ants detect this trail and follow it, each one reinforcing the scent as they travel. As more ants follow successful paths, those roots become stronger through accumulated chemical signals. Roots leading to depleted resources gradually fade as fewer ants reinforce them. This creates a dynamic, self-updating map of opportunities in the environment. The entire colony optimizes its foraging routes in real time, without any ant understanding the overall pattern. When food sources shift, when new opportunities appear, when dangers emerge, the chemical network adapts almost immediately. Individual ants contribute their small pieces of information through simple behaviors. The colony as a whole solves complex optimization problems that would challenge sophisticated algorithms. This decentralized communication system allows the collective to respond to changes with remarkable speed and efficiency. In the silent exchange of molecular messages, written in scent across the landscape, ants build shared knowledge that guides thousands toward success. A concept in your mind doesn't exist in a single location like a file stored in a computer. Instead, it lives as a distributed pattern of activity spread across many brain regions simultaneously. When you think about something, clusters of neurons in different areas activate together, each contributing a different dimension of meaning. Some regions add sensory qualities, the way something looks or sounds or feels. Others contribute emotional associations, memories of how you felt when you first encountered the idea. Still others provide abstract structure, relational information, connections to other concepts. Together, these dispersed activations create a rich, multifaceted representation. Because these patterns overlap and intermingle, concepts naturally influence each other. The boundaries between ideas remain fluid rather than rigid. This distributed organization allows remarkable flexibility in thinking. The same concept feels different depending on context, emotional state, or what other ideas are active simultaneously. When creativity flows, it often comes from unexpected overlap between concept patterns, from moments when representations that don't usually activate together suddenly find themselves sharing neural space. Your mind navigates landscapes of meaning rather than retrieving fixed entries from mental storage. Along rocky coastlines where waves crash and retreat, sea otters float on their backs with stones balanced carefully on their chests. They strike shells against these anvil stones with practiced precision, cracking open stubborn prey that couldn't be accessed any other way. Young otters watch these performances with intense concentration, studying how adults select appropriate stones, how they position themselves in the water, how they adjust the force of their strikes. Eventually, the young begin experimenting, choosing stones of different sizes and weights, testing various grips and striking angles. Through observation and practice, they gradually master techniques that aren't encoded in their genes, but must be learned socially. Different groups develop preferences for particular stone types or distinct methods for handling different prey species. These techniques become family traditions, passed down through generations, not as genetic inheritance, but as cultural knowledge. Mothers teach daughters, who will later teach their own offspring. Over time, local variations emerge, creating distinct cultural identities among different otter communities. This transmission of tool-use knowledge demonstrates a cognitive capacity for cultural learning that binds communities together across time, showing that intelligence in the ocean extends beyond instinct into realms of tradition and social memory. Human imagination works by taking fragments of actual experience and recombining them into patterns that have never existed in reality. When you imagine something new, your mind doesn't create from nothing. Instead, it gathers pieces from your stored memories and assembles them in novel arrangements. A smell from childhood might merge with a place you visited last year. An emotion from one conversation might blend with a visual image from somewhere else entirely. These fragments, drawn from different times and contexts, combine to create scenarios, ideas, and possibilities that feel fresh and original. This blending process relies on brain networks that bridge different types of memory storage. Sensory details stored in one region connect with emotional learning in another, with abstract concepts in a third, with motor memories in a fourth. Imagination becomes a space where past experience transforms into new patterns through endless recombination. This ability allows humans to envision inventions that don't yet exist, to write stories about events that never happened, to plan futures that may never come to pass, to solve problems by mentally testing approaches before trying them physically. By reorganizing the pieces of lived experience, the mind constructs entire worlds that exist only in thought. Gliding through warm ocean currents with wing-like fins extended, manta rays sometimes approach unfamiliar objects with what appears to be genuine curiosity. Rather than fleeing or attacking, they circle slowly, adjusting their position and distance as though studying details carefully. When they encounter reflective surfaces, some individuals engage in exploratory movements that seem investigative rather than territorial or aggressive. They turn gracefully, changing angles to view reflections from different perspectives. They pause and hover, as though contemplating what they're seeing. In open water, they also investigate novel shapes, lights, and textures with sustained attention that goes beyond simple novelty response. This behavior suggests more than attraction to new stimuli. It hints at a deeper form of curiosity, where the animal explores not just the environment, but perhaps its own relationship to that environment. The calm, deliberate nature of their investigations reflects a quiet intelligence that remains largely mysterious to researchers. In the gentle movements of these massive creatures, in their patient examination of their surroundings, there is a quality that resembles introspective awareness, as though they possess some form of wondering about the world they inhabit. Your brain learns complex skills through internal simulation, running mental rehearsals over and over, even when your body remains completely still. Before a musician performs a difficult passage, before an athlete attempts a complex sequence, before a speaker delivers important words, the mind often practices silently. These mental rehearsals activate many of the same neural circuits that control actual movement and speech. Timing patterns strengthen, sequential coordination improves, muscle memory forms even without physical motion. A pianist can practice fingering patterns while sitting motionless. A dancer can refine choreography while lying in bed. A chess player can explore strategies without touching a single piece. Each internal repetition strengthens the neural pathways that will guide real performance. The simulation allows unlimited practice without fatigue, without risk of injury, without needing space or equipment. When the actual moment arrives, the body and mind execute movements that have been refined through countless invisible rehearsals. This transforms imagination into a form of training, turning the mind's theater into a workshop where mastery develops through patient, repeated simulation. In colonies where millions of insects live and work together, memory doesn't reside in individual minds, but in the collective patterns of movement and behavior. When environmental conditions shift, when threats appear, when resources change, the entire colony adjusts its activity in coordinated ways that persist over time. These collective patterns serve as a form of memory, The colony remembers through coordinated action rather than neural storage. When similar conditions appear again, the colony responds with patterns shaped by previous experiences. The rhythm of activity changes, movement flows shift, priorities reorder themselves. No individual insect stores the complete memory. Instead, each contributes to a living record of events written in the movements of thousands. This distributed memory allows groups to navigate challenges with precision that no single member could achieve, turning the colony into a thinking entity whose knowledge lives in coordinated behavior rather than individual recall. Creative insights often emerge when brain systems responsible for executive control temporarily relax their grip. The networks that maintain focus, suppress irrelevant thoughts, and direct attention toward specific goals are crucial for many tasks. But they can also create mental rigidity that blocks novel connections. When these control systems ease, when discipline softens, the mind gains access to a wider range of associations. Ideas that normally stay separated begin drifting toward each other. Distant memories surface. Unlikely combinations form. This mental loosening often happens during restful activities like walking, showering, or drifting towards sleep, when external demands fade and internal constraints relax. In these moments, creative insight can crystallize. Elements that seemed unrelated suddenly align in meaningful patterns. Solutions appear to problems that resisted focused effort. Once the insight emerges, executive control returns, helping to stabilize and develop the new idea. Creativity flourishes in this dance between freedom and structure, where relaxation opens doors that discipline then helps to build into something lasting. On coastal sands beneath vast open skies, certain crabs navigate with surprising precision using cues that reach them from the heavens. They detect the position of the sun even when it is hidden behind clouds, reading subtle polarization patterns in lights scattered across the atmosphere. These faint gradients reveal the hidden direction of sunlight, providing navigational information even when direct visual cues are obscured. As crabs scuttle across beaches and through tidal zones, they continuously adjust their paths based on celestial information. Their tiny nervous systems process these complex optical signals, extracting directional meaning from patterns of light polarization that human eyes cannot detect without special instruments. This reliance on sky-based guidance allows them to travel long distances with reliable accuracy, finding their way home after foraging expeditions, locating favorable tidal zones, avoiding dangers. In their small bodies operates a form of natural astronomy, an instinctive understanding of how light moves through the atmosphere that allows confident navigation through a world shaped by tides, shadows, and the slow movement of the sun. Human learning strengthens dramatically when experience violates expectations, when reality delivers surprises that don't match predictions. In those moments of mismatch, neural circuits involved in attention, error detection, and memory formation surge into heightened activity. Neurochemicals that support learning flood the synapses, marking the surprising event as important and worthy of deep encoding. The mind stops relying on automatic processing and instead examines the unexpected information with sharper focus. It compares the surprise against existing knowledge, searching for explanations, updating internal models to accommodate the new evidence. Lessons connected to surprise get stored more deeply and retrieved more easily because they carry markers of significance. Over a lifetime, experiences rich in gentle surprises build minds that update themselves readily, that remain flexible and open to correction, rather than clinging rigidly to comfortable assumptions. Each surprise becomes an opportunity for growth, a moment when the brain reorganizes itself to better match the complexity of reality. In laboratories and research facilities, robots equipped with self-organizing learning algorithms develop movement strategies and problem-solving, approaches that human engineers never anticipated. Designers set basic goals and constraints, then allow the machines to adjust their own internal parameters through extensive trial and error. Given enough time and variation, these systems discover solutions that appear strange to human intuition, yet perform remarkably well. A robot might develop an unusual gait that looks inefficient, but actually conserves energy over long distances. Another might discover a sequence of actions that exploits tiny environmental details in ways no human would have conceived. When researchers analyze these machine-discovered strategies, they often find that the approaches obey principles that were invisible before the robot uncovered them. The machines become collaborators in discovery, expanding the space of known solutions beyond what human designers could imagine alone. This reveals that intelligence, even artificial intelligence, can venture into territories of possibility that remain hidden from individual human minds, finding answers in spaces we didn't know existed. As you move through familiar environments, specific groups of neurons in your brain fire in patterns that map your position and orientation. Some cells activate only when you occupy particular locations. Others respond to the direction you are facing. Still others fire in response to boundaries, corners, and landmarks. Together, these different cell types create an internal coordinate system, a neural grid that tracks where you are and how you are oriented within space. This grid doesn't use measurements like meters or feet. Instead, it operates through rhythmic patterns and sequences of neural activity that shift continuously as you move. When you later recall a route, these same patterns replay in modified form, reconstructing the spatial structure of your memory. You can mentally navigate through places you are not currently in, following remembered paths, anticipating turns, estimating distances, all through the activation of these internal spatial codes. Your sense of location lives not as a picture or map, but as a living choreography of electrical pulses, a neural dance that traces the structure of the world inside your mind. In complex primate societies, individuals engage in behaviors that look strikingly like rudimentary politics. They track alliances between group members, trade favors and support, manage their social reputations carefully. A monkey might groom a particular companion specifically to secure that individual's support in future conflicts. Some choose strategic moments to back certain allies, strengthening bonds that will later provide protection or access to resources. Others reconcile after fights with gestures clearly designed to restore trust, apparently recognizing that prolonged hostility weakens both parties. Still others observe tensions carefully and choose when to intervene, gaining influence without constantly taking direct risks. These behaviors require memory for past interactions, ability to predict how others will respond to different actions, and understanding of how relationships combine to shape group dynamics and stability. In the shifting web of glances, gestures, grooming partnerships, and temporary coalitions, an early form of strategic social reasoning emerges. This political intelligence foreshadows human negotiations, alliance building, and the complex social calculations that characterize our species, showing that such thinking has deep evolutionary roots, extending back through our primate heritage. Human intelligence expands when we engage with ideas positioned just beyond our current understanding, in that productive zone where comprehension requires genuine effort, but remains achievable. When concepts are too easy, we learn little. When they're impossibly difficult, we give up or learn only confusion. But in between lies a sweet spot. In this zone, the brain must recruit additional resources to grasp the new material. Working memory, sustained attention, and reasoning processes coordinate more tightly. As you struggle productively with challenging ideas, your mind forges new connections between existing knowledge and unfamiliar structures. Each partial success reinforces motivation, while revealing exactly where your understanding remains incomplete. Over time, repeatedly engaging with material just beyond current ability expands cognitive capacity. People who regularly seek out such challenges gradually build more complex and sophisticated mental frameworks. Intelligence grows not from staying comfortably within what you already know, but from repeatedly reaching toward the edge of comprehension and pulling new understanding back into your grasp. During carefully designed experiments, certain parrot species demonstrate an ability that parallels a crucial stage in human cognitive development. When shown pairs or groups of objects, these birds can judge whether items match in specific properties like color, shape, or number, even when the particular objects are completely new. They're not memorizing correct responses for familiar combinations. They're applying abstract rules about sameness and difference that transcend specific examples. When presented with novel items, they can still indicate which ones share a property and which don't, showing genuine conceptual understanding. Human children pass through similar developmental stages as they learn to classify and compare. That parrots reach this capability through entirely different evolutionary paths, using brains organized completely differently, reveals that the capacity for abstract comparison doesn't belong exclusively to primates. The roots of conceptual thought can appear in feathered minds as readily as in mammalian ones. In some organisms, the immune system carries traces of past experiences that influence not just disease resistance, but also behavioral and neural responses. Immune cells adapt to repeated exposures, and their changed states can alter the chemical environment in which neurons operate. Over time, patterns of immune activity create a subtle record of what an organism has endured. This record is written not only in synaptic connections, but in circulating cells and signaling molecules throughout the body. The immune system's state shapes baseline stress responses, influences emotional reactivity, affects how the nervous system processes information. In certain cases, these patterns can even influence offspring, who inherit bodies already tuned by parental experiences. Memory spreads beyond the brain, distributed through the entire organism. Intelligence becomes a phenomenon involving the whole body's learning from the world, showing that mind and body are far more integrated than simple brain-centered models suggest. When you feel yourself making a choice, when you experience that moment of decision, many processes have already unfolded beneath conscious awareness. Sensory systems have gathered information. Emotional centers have weighed values and significance. Motor planning regions have begun preparing for action, tilting toward one possibility or another. These processes occur rapidly, mostly outside awareness. Only when they reach a certain threshold does conscious experience catch up, delivering that subjective sense of deciding. Awareness arrives like a narrator joining a story already in progress, describing and sometimes adjusting outcomes, but never starting from a blank slate. This doesn't eliminate the meaning of choice or the reality of responsibility. Instead, it reveals that conscious will operates as part of a broader, layered system where reflexes, habits, learned patterns, and deep evaluations all contribute. The feeling of deciding is the moment when this hidden activity becomes visible to itself, creating opportunities for reflection and intentional adjustment. Across vast savannas, elephant herds maintain coordination, even when individuals are separated by considerable distances. They achieve this through vibrations that travel through the ground, rather than only through air. Low-frequency rumbles and deliberate stomps create seismic signals that propagate through soil and rock. Elephants detect these ground vibrations through sensitive receptors in their feet and trunks. This allows them to sense the movements and calls of distant companions that may be completely out of sight. Through this channel, they coordinate group travel, warn of dangers, guide separated members back to the group. Young elephants learn to interpret these vibrational messages by following experienced adults and feeling the subtle tremors underfoot. Over long distances, this seismic communication knits the herd into a coherent whole. Even when members scatter across kilometers of landscape, the Earth itself becomes a medium for shared awareness, carrying information between massive bodies that move as one organism distributed across the land. Human creativity may depend on brain networks that simultaneously compete and cooperate in a delicate ongoing tension. Some neural systems specialize in focus, planning, and goal-directed control. Others favor imagination, free association, and unconstrained exploration. During creative work, these networks don't simply alternate. They engage in dynamic interaction. Imaginative systems generate possibilities without worrying about practicality or rules. Control systems evaluate, refine, and select among the options presented. Sometimes they oppose each other as discipline tries to suppress wild ideas and daydreaming resists constraint. Yet when creativity flows optimally, they achieve a subtle balance. The exploratory networks roam widely, but remain loosely tethered to purpose. The controlling networks relax just enough to permit novelty without dissolving into chaos. This ongoing negotiation between freedom and structure gives creative thinking both originality and coherence, allowing genuinely new forms to emerge while maintaining enough organization to make them meaningful and communicable. In shifting underwater environments where tides and currents constantly reshape the landscape, cuttlefish maintain remarkably detailed memories of places they visited. They remember not just locations, but the circumstances surrounding each experience, including contextual details like time of day and environmental conditions when events occurred. When returning to familiar areas, cuttlefish behave as though consulting an internal timeline. They adjust their actions based on both location and context, showing understanding that circumstances change over time. A hunting ground that was productive in the morning might be empty in the afternoon. A hiding place that was safe yesterday might be dangerous today. This form of memory appears to function like episodic memory in humans, where events are remembered as specific episodes embedded in time and place rather than as isolated facts. Cuttlefish use these detailed recollections to predict which areas might still offer prey, which hiding spots remain safe, which predators might be nearby. Even as they age, they maintain this capacity with impressive clarity, showing memory preservation rare among invertebrates. Their intelligence emerges through sophisticated integration of perception, recollection, and anticipation. Throughout each waking day, your brain absorbs countless fragments of information that never reach conscious awareness. Subtle patterns in overheard conversations, glimpsed visual regularities, rhythms sensed during routine activities, all settle quietly into neural circuits. When sleep arrives, these fragments become active again. During different stages of sleep, brain networks replay traces of waking experience, sorting through the day's acquisitions. Deeper sleep stages strengthen patterns deemed valuable, linking them with related knowledge and slowly integrating them into more stable long-term storage. This nocturnal processing strengthens learning that felt vague or incomplete during waking hours. People often awaken with improved understanding of concepts that resisted comprehension the previous day. Musicians find passages easier. Language learners speak more fluently. Problem solvers see solutions more clearly. Sleep serves as an invisible teacher, refining and consolidating knowledge in hidden hours. When conscious awareness fades and internal rhythms carry the mind toward deeper integration and understanding. In sandy plains beneath clear, shallow waters, certain fish species create intricate circular formations that reveal sophisticated understanding of geometry and spatial relationships. They construct these structures by repeatedly sweeping sand with their fins, creating ridges and valleys arranged in elegant symmetrical patterns. The formations span impressive distances and require sustained effort to maintain. Fish work tirelessly, adjusting the depth of grooves, managing symmetry, orienting their bodies in deliberate arcs. They return again and again to refine sections until the entire structure achieves balanced proportions. Although driven by instinct to create these formations for mating displays, the fish demonstrate spatial awareness and geometric sense as they monitor angles, align contours, and correct disturbances from currents and shifting sand. They must hold the blueprint in memory throughout the construction process, maintaining consistent spacing and adjusting each segment in response to environmental changes. The resulting underwater mandalas function as both art and communication, demonstrating how motor intelligence and spatial reasoning can create beauty, even in creatures whose minds operate on entirely different principles than our own. Within your brain, intelligence emerges not from any single powerful network, but from interactions among countless smaller systems working in shifting coordination. Miniature networks operate simultaneously throughout your nervous system, each performing specialized tasks. Some process sounds, others handle visual patterns. Still others store temporary information, evaluate emotions, construct language, or connect present experiences with memories. No single network carries intelligence alone. Instead, thought emerges from dynamic alliances formed between circuits. During reflection, networks synchronize their rhythms, exchanging signals through intricate pathways. When challenges appear, systems that typically work independently may join forces temporarily, creating coalitions that produce novel insights. Once the challenge passes, these alliances dissolve and networks return to their usual patterns. This constant formation and reformation of temporary partnerships allows the human mind to adapt with remarkable speed and flexibility to changing circumstances and novel problems. Intelligence lives in the harmony created by countless contributors, in the emergent properties of networks that cooperate, compete, and coordinate in an endless dance of neural activity. Young songbirds, learning their species' melodies, spend daylight hours absorbing adult songs. These songs carry crucial social information, marking territory and announcing individual identity. When night falls and the forest quiets, the learning continues in a different form. During sleep, neural circuits governing vocalization replay fragments of the day's song. These internal rehearsals occur without physical sound production, yet they activate the same sequential patterns that control actual singing. Through nocturnal practice, the young bird adjusts pitch, timing, and rhythm, transforming scattered notes into coherent melodies. When dawn arrives, the bird awakens with improved vocal control shaped by work performed in dreams. This silent refinement continues for weeks or months, depending on the complexity of the species' song. By the time the bird sings confidently to greet sunrise, its melody carries the imprint of countless rehearsals woven through many nights of sleep. When confronting difficult problems, the brain sometimes achieves better results by shifting into states that use less energy rather than more. During high-stress, intense effort, neural activity can become noisy and disorganized, actually interfering with problem-solving. But when the mind settles into calmer, more organized patterns, thinking often becomes clearer. In these energy-efficient states, unnecessary neural firing decreases, while activity concentrates along pathways most relevant to the problem at hand. Information flows with greater clarity. Subtle connections emerge that would be overwhelmed during periods of high activation and mental strain. Many breakthroughs occur during moments of quiet reflection rather than forceful thinking because the brain reaches optimal efficiency when tension relaxes. Complex relationships surface naturally in this calmer state, revealing a deeper form of intelligence that depends on harmony and balance, rather than intense effort. Living in intricate social groups, monkeys observe each other with constant attention to detail. Every gesture potentially carries meaning. A relaxed movement may indicate peaceful intent. A hesitation might reveal uncertainty. A shift in posture could signal an impending challenge. Through continuous exposure to these subtle cues, monkeys develop sophisticated abilities to infer intentions from minimal information. They adjust their own behavior based on these interpretations, choosing when to support allies, when to avoid potential conflicts, when to initiate cooperation. This skill parallels early stages of social understanding in human children, who also learn to read intention from motion and gesture rather than explicit verbal instruction. For monkeys, this perceptive ability strengthens group cohesion, allowing smoother interactions in environments where misunderstanding could lead to serious conflict. Their social intelligence emerges naturally from lives filled with observation, interpretation, and adaptive response to the constantly shifting dynamics of group life. During moments of deep, meaningful conversation, when two people engage genuinely with shared ideas and emotions, something unusual can happen. As attention intensifies and emotional resonance grows, brain rhythms in both individuals begin following compatible patterns. This synchronization reflects more than simple agreement. It emerges from simultaneous engagement with the same concepts, creating a temporary shared mental landscape. Communication becomes fluid and effortless during these moments, as though each person understands the other with unusual clarity and depth. The alignment strengthens when trust deepens, when the conversation touches on subjects that matter profoundly to both participants. Although brief, these periods of neural synchrony reveal how deeply social human cognition truly is, showing that thought can extend beyond individual boundaries, forming bridges between minds through the simple but powerful act of genuine connection. Young wolves absorb the unwritten rules governing pack life by watching conflicts unfold around them. They observe disputes over food, rank, and territory with unwavering attention. Each confrontation teaches different lessons about hierarchy, about which individuals command respect and which yield, about how tensions resolve without lasting damage. They note the postures that signal challenge, the gestures that restore peace, the precise timing that determines whether interactions escalate or dissolve. Through these observations, wolves build internal frameworks for understanding social dynamics and their own future roles. Eventually, they adopt behaviors that maintain harmony, reduce unnecessary violence, and strengthen group unity. Their understanding of social balance develops gradually, shaped by countless moments of watching, learning, and absorbing the complex rules that govern pack stability and cooperation. Throughout life, human brains develop rapid mental shortcuts based on recurring patterns in the environment. These shortcuts guide decisions with impressive speed, allowing quick responses in complex situations where thorough analysis would take too long. A slight shift in someone's vocal tone signals emotional change. A faint environmental cue reveals a hidden pattern. A familiar structure appearing in a new situation suggests a likely outcome. These shortcuts don't represent carelessness or laziness. They reflect deep familiarity accumulated through years of experience. Though they occasionally mislead, they generally function well in environments similar to those where they developed. They allow humans to act quickly and often accurately in situations too complex for deliberate step-by-step reasoning. These patterns reveal how intelligence extends beyond conscious deliberation, operating through quiet forms of knowledge gathered and refined across lifetimes of experience. In certain dry landscapes where fire moves through grassland seasonally, a few bird species have learned to exploit flames in ways that suggest genuine causal understanding. When wildfires sweep through tall grass, these birds wait at the edges for insects fleeing the heat. But their behavior goes beyond opportunistic feeding. They sometimes pick up burning sticks or smoldering embers, carry them to unburned vegetation, and drop them deliberately into dry fuel. The resulting fire flushes out insects, creating new hunting opportunities. For this to work, the bird must predict that a burning fragment will ignite fresh material, that flames will spread through grass, that prey will scatter as fire advances. The bird must also handle the ember carefully enough to avoid injury, while placing it where ignition is most likely. This suggests understanding of cause and effect sophisticated enough to model how fire behaves under different conditions. Such knowledge cannot rely purely on instinct, because the technique must adjust based on wind, fuel moisture, and temperature. It is learned through experience and experimentation, with a dangerous element that transforms entire landscapes. Human intelligence may expand when we construct mental models of entire interconnected systems, rather than focusing only on isolated components. When people attempt to understand only individual details, their thinking remains narrow and limited. But when they begin building internal representations of how multiple elements interact within larger systems, their intelligence deepens and extends. A system might be an ecosystem, a social community, a scientific principle, or the workings of a complex machine. Building such models requires tracking relationships among many moving parts, anticipating how changes ripple through the structure, adjusting predictions as new information arrives. This process strengthens neural areas involved in reasoning, working memory, and abstraction. It encourages flexible thinking, because systems rarely behave in simple linear ways. People who habitually form broad mental models grow better at planning, innovation, and adaptation. They detect hidden patterns in complexity and foresee outcomes that escape minds focused only on fragments. By holding entire structures in mind simultaneously, they allow intelligence to operate across layers of reality rather than remaining confined to isolated points. In primate groups, individuals maintain detailed memories of social exchanges, spanning years. They remember who offered support during difficult times, who shared food during scarcity, who withheld help when it was needed. These memories shape long-lasting social strategies and relationships, A primate that received grooming during hardship may later assist the benefactor in a territorial dispute months or years afterward. Another that was ignored during need may quietly withhold support when the neglectful companion later seeks help. These exchanges unfold not through immediate reciprocation, but through patient tracking of social debts across time. This requires judgment, memory, and ability to connect past behavior with future decisions. It also requires restraint, recognizing that maintaining social bonds provides benefits extending far beyond single encounters. Over years, these accumulated debts and credits form the foundation of alliances, peacekeeping, and stability within groups. The intelligence behind these exchanges shows that primates perceive social life as an intricate web of obligations that must be honored to preserve harmony and cooperation. The human mind stores information with vastly different strengths, depending on personal relevance and emotional connection. Facts learned in isolation without context or meaning often fade rapidly from memory. They slip away almost as easily as they entered, leaving barely a trace. Yet, when new knowledge resonates with personal experience, connects to existing interests, or carries emotional significance, memory deepens dramatically. The brain binds fresh information to establish networks of meaning, weaving it into the fabric of identity and lived experience. This connection activates areas involved in emotion, narrative construction, and long-term consolidation, anchoring new material far more firmly than rote repetition ever could. Students who link abstract concepts to personal curiosity retain them longer. Readers who relate story characters to their own experiences remember narratives vividly. Anyone who ties lessons to lived experience strengthens retention almost automatically. Meaning becomes the thread that stitches knowledge into lasting form, transforming memory from passive storage into active integration with one's sense of self and understanding of the world. Far from coastlines, crossing vast expanses of featureless ocean, certain shark species navigate with astonishing precision, often returning to the same feeding or breeding grounds year after year across thousands of miles. They achieve this through sensitivity to Earth's magnetic field. Specialized cells in their bodies detect subtle variations in magnetic intensity and orientation. As they swim, they gather information about the magnetic signature of each region, gradually constructing internal maps of the invisible structure underlying the ocean. This magnetic sense functions like a natural compass overlaid on a global positioning system. When currents shift or storms disrupt familiar routes, sharks still locate destinations by referencing the planet's magnetic architecture. This ability requires more than instinct because magnetic fields vary with depth, location, and geological features. Sharks interpret these variations, update their internal maps, and adjust their courses accordingly. Through this remarkable navigation system, they traverse an environment with no visible landmarks, guided by ancient intelligence attuned to the fundamental magnetic fabric of Earth itself. Human insight often accelerates during periods of mental rest between intensive thinking sessions. When the mind reaches overload during demanding cognitive work, further effort frequently produces only confusion and frustration. Yet when people step back, allowing rest or shifting focus to something gentler, insight often crystallizes with unexpected clarity. This happens because rest allows neural networks to reorganize information without the pressure of conscious forcing. Systems that were overwhelmed during intense concentration settle into more coherent patterns. Hidden relationships among ideas strengthen, while irrelevant noise fades into the background. As the mind relaxes, fragments of understanding drift into new configurations, forming structures that were inaccessible during strain. This explains why breakthroughs so often happen during walks, showers, quiet moments, or gentle activities, rather than at the peak of effortful concentration. Rest is not absence of thinking. It is the space where deeper connections form beyond deliberate awareness, where insight rises naturally from the quiet depths of unconscious processing. In dense rainforests where resources hide and paths twist unpredictably, orangutans face challenges, demanding more than instinctive responses. They encounter obstacles blocking food sources, problems requiring tools, situations needing creative solutions. Instead of relying only on learned routines, they improvise. An orangutan may select a branch of particular thickness to test whether a crossing is stable. It might strip leaves from a twig to create a tool for extracting insects or accessing sap. Sometimes it combines several objects to achieve a specific goal, demonstrating ability to imagine future outcomes and plan toward them. This foresight reflects sophisticated causal understanding. When circumstances change, orangutans adapt their strategies. If a tool breaks, they select a better one. If the environment shifts, they modify their approach. Their improvisation emerges from observation, memory, and flexible intelligence, shaped by the complex demands of forest life, showing that planning and foresight extend deep into our evolutionary heritage. Human creativity and innovation flourish when individual minds contain diverse kinds of knowledge from multiple domains. When ideas from unrelated fields coexist in the same person, they generate combinations and insights that would never emerge from narrow specialization. Someone understanding both art and mathematics may discover patterns invisible to those knowing only one. Someone familiar with storytelling and engineering may find solutions blending imagination with technical precision. Within the mind, different domains interact, compare, merge, and reshape each other. This internal diversity strengthens cognitive flexibility, broadens perspective, and encourages novel thinking that crosses traditional boundaries. The more varied the internal landscape of knowledge, the more pathways exist for intelligence to travel. The more connections become possible, the greater the potential for breakthrough insights that recombine existing knowledge in transformative ways. During experiments testing abstract reasoning, pigeons demonstrate abilities that challenge assumptions about cognitive complexity and brain size requirements. They learn to categorize objects, not by memorizing individual examples, but by identifying general principles, applying across many variations. They distinguish patterns involving relative properties like size, shape, and brightness, even when specific items change completely from trial to trial. These performances reveal that pigeons grasp abstract concepts, applying rules flexibly rather than through simple repetition. Their success shows that intelligence doesn't depend solely on large brains or complex cortical structures. What matters is neural organization and processing efficiency. The pigeon brain handles visual information with remarkable effectiveness, allowing these birds to understand relationships among objects that appear completely different, forcing scientists to reconsider how widespread abstract reasoning may be throughout the animal kingdom. Human intelligence has evolved through cultural transmission that changes far more rapidly than genetic inheritance ever could. Each person develops within a cultural environment that passes knowledge across generations at speeds impossible for biological evolution. Every individual inherits not only a body shaped by ancestry, but a world filled with accumulated wisdom, stories, tools, symbols, techniques, practices created by countless predecessors. Culture functions as external memory, extending far beyond individual cognitive capacity. As people learn from one another, they refine ideas, expand skills, deepen collective understanding. Cultural evolution allows innovations to spread quickly, accumulating layer upon layer of shared insight. While genetic changes require vast timescales, cultural knowledge transforms within single lifetimes. This rapid exchange shapes how humans think, solve problems, imagine possibilities. Intelligence becomes a product of collaboration spanning centuries, woven from contributions of many minds acting together across time. Long before children understand word meanings, their brains absorb the statistical structure of language flowing through their environment. As speech washes over infant senses, neural systems begin detecting which sounds tend to appear together, which combinations occur frequently, which sequences are rare. This process unfolds automatically, revealing extraordinary pattern detection abilities. Even in noisy environments, the infant brain isolates syllables and probabilities, gradually establishing boundaries between words that were never presented as separate units. Babies exposed to multiple languages simultaneously keep patterns distinct, showing that minds can track several sound systems at once. Learning continues as the brain strengthens connections representing useful regularities, while pruning those that don't appear in the linguistic environment. Meaning layers onto this foundation later, built upon underlying architecture, formed through recognition of subtle acoustic patterns. Language acquisition begins not with vocabulary but with pattern detection, so refined it transforms continuous sound into maps of communication. When researchers train advanced artificial neural networks to solve complex tasks, these systems often develop strategies no human designer anticipated. Networks reorganize information, build internal representations, discover shortcuts and solutions that emerge from their architecture and training without explicit programming. They cluster similar concepts, compress data into meaningful structures, form layers of abstraction, helping them navigate novel situations. Sometimes their internal workings echo patterns found in biological brains: sparse coding, modular organization, gradual refinement of predictive models. These parallels emerge because both artificial and biological systems face similar challenges: interpreting complex environments. Each must filter noise, detect relevant structure, form stable predictions. Artificial networks achieve this through vast numbers of simple units working together, while biological networks rely on neurons shaped by evolution. The similarities suggest intelligence may follow certain universal principles whenever systems must learn from experience, regardless of whether they're made from silicon or living cells.